Okay, well, we may have, I hope a few more arrive, but just in case, somehow when there are 11 of you here at 2 till 8, it was like, maybe it was 13, but I don't know that we're all going to make it. Okay, today we're going to look at functions. And we're ultimately going to look at them in a different way than we've looked at them before, but as we think back to functions, what do you remember about functions? Okay, input, output. So we can kind of draw something like this, and so we input something and we get an output. Or we can put it in a table of inputs and outputs. Or sometimes even another picture the book uses, say an input set, and what do we match with? So we get a set of inputs and a set of outputs. So we've got a few different sort of models that kind of illustrate input, output. What we typically think of as a function, though, I would say is y equals f of x, some rule. Say y equals x squared. The rule that tells us put in an input, do something to it, and we get an output produced. Now, with this picture and with this idea, there's a couple things we have to watch for that maybe you remember, maybe you don't. But one of the things we have to watch for is, say, 2, 3, and 2, 4. If we repeat the inputs, we do not have a function. The whole idea of a function is for each input, there's exactly one output. We may repeat outputs, but we cannot repeat the inputs and have a function. We can put together a table, but in terms of thinking as the function is, say, doing some job, no, this is a problem. What do we do with 2? Well, maybe we produce 3, maybe we produce 4. We don't really know. So technically a function from a set A to a set B is, we could call it a rule that assigns to each element A and A exactly one element B and B. And the two keys here are each input is paired with exactly one output. And to kind of illustrate that, my 2 favorite functions to illustrate that, and for those who've had me before and have heard this illustration, you get to hear it again. But my 2 favorite illustrations for this are the gradebook function and the sheetbook function. And the gradebook function, set A is the class roster, and set B is the set of grades. And so I'll start assigning grades. No guarantees, promises, threats with any of this, just for illustration purposes. What would create a problem in this, though, is if I go, say, Austin A and Austin C. Repeating the input is a problem because in the gradebook function, I turn that in, the registrar is going to say, what grade did Austin get? Well, I want to give him both. Now, I can't give him both. I've got to pick a grade for that. Another thing that would be a problem would be, say, this scenario. I don't turn in a grade for Josie. Registrar would say, well, what's Josie's grade? Well, I didn't want to give her one. Well, if she's in the class, I've got to give her one. So the rules got to assign to each input, so we can't skip any of the inputs, exactly one output. We can't repeat the inputs. We can repeat the outputs, and in fact, for the gradebook function, I have to. I can't give you all different grades. I don't have that many grades available to me. Thankfully, I don't. And it would be really hard, I think, to work with that. You know, in one class, you were number 2 out of 30. In one class, you were number 2 out of 3. You know, what does that say about your performance in the 2 classes? Well, somebody did better than you in both classes, but we've settled on grades rather than, well, let's just rank everybody from top to bottom and assign grades based on that. So that's the gradebook function in terms of illustrating that. The sheep goat function, our set A is the set of all people, and B is a fairly simple set. B is the set containing just sheep and goats. In Matthew, there's a verse, and he'll separate people at judgment, much like a shepherd separates the sheep from the goats. And again, as people are identified, we're never going to have anybody paired both ways. The inputs won't be repeated, and nobody's not going to be on the list. Everyone will be identified as a sheep or a goat with that. And so each input is paired with exactly one output. Now, the input being paired, each input, there are a few things I can do back here in this gradebook function. If it really was true that for some reason I thought Josie shouldn't have a grade, I could argue, well, she should never have been on the roster in the first place. She came twice, she stopped attending, something like that. So maybe I could get her out of the set A. But if I have a function, every element in set A has got to be paired with something in set B. Now, in the classes we've worked with, algebra, calculus, we typically did one of two things with functions. We would either, this rule, so we would got the set A and the set B. We either start from the input and try to figure out the output, what I would call evaluate, or we'd start from the output and try to figure out, well, where did it come from? Which I would call solve. And in this particular one, the solving is not necessarily unique. An output could have come from more than one place. It's also possible that what we think might be an output didn't actually come from any place at all. So if we look at the sets A and B, the set A is the domain. It's called the domain. And the set B is called the codomain. The range of the function is the set of actual outputs. And that would be a subset of the codomain. But it wouldn't have to be the entire codomain. Just because I can use the grades A through F doesn't mean I have to give anybody an A or an F. Just those are the grades I can use. So in terms of the domain, we only put things in the domain that we really are going to assign to something, but in the codomain, we don't necessarily have to get all the possible outputs. I think in the sheep goat function, God's desire would be there'd be no goats. I mean, that's why he sent his son, so that all who accept can be saved, but not everyone accepts that offer of salvation, so I believe there will be goats. But the codomain is the set of possible outputs. And usually as we look at this in calculus, the domain is the set of all reals or some smaller set, so that we don't divide by 0 or don't do square roots of negatives. And the codomain is usually set of all reals. And we just let all reals could be outputs, although then typically we would do some working. Can we figure out what the outputs are? What we're going to do with functions, though, is not so much just evaluate them. But we're going to be looking at functions kind of in their own right. So let's look at a fairly small example, but a fairly abstract example. Suppose A is the set 1, 2, 3, and B is also the set 1, 2, 3. And F is some function from A to B. So we've got the inputs 1, 2, 3. We're going to produce outputs from the set 1, 2, 3. Can somebody think of one function? Where can we send 1? We could send it to 1. Where can we send 2? Well, okay, we could send it to 2. Well, let's go ahead and send 3 to 3. I mean, that is a function. It's not a very exciting function. In fact, we call this the identity function. It doesn't do anything. It leaves all the inputs unchanged. And in terms of where we're headed, actually, this is a very important function. There's a reason we call it the identity function. But is it the only function? So do you have another one in mind?
Y equals 4 minus x.
Yeah, well, I'm not even necessarily thinking a rule, because we're just... So 4 minus x, so there's what, 3, 2, 1?
Yeah.
Okay. And we can do that with a rule. So this is one function, this is one function. How many of these do you think there are? As many as we want. Somebody else looks troubled by that.
Wouldn't it just be kind of like,
Huh?
wouldn't it just be 3 by 3?
Okay, so you say 3 by 3, so...
Well, each element can have each output 3 times, and there's 3 elements.
And there's 3 elements.
But they can't.
Okay. So is that 3 by 3, or is that
I think it'd be 3 factorial.
3 factorial? Any other? I would agree with what you've said there so far. We have 3 choices for this one. We have 3 choices for this one. And we have 3 choices for this one. How many choices is that altogether? At this point, yes. So, which is why there's 3 choices for all of them. If they can't repeat, we'd have to modify this. So just in terms of functions, send 1, 2, 3 to some element in 1, 2, 3. They could all go to 1. That would be a function. Send them all to 1. Send them all to 2. So I mean, we've got a number of possibilities. What we're trying to figure out is, well, how many? I hear 27. 3 times 3 times 3, 27 different choices. So there are 27 different functions. Well, with that, we're going to need some somewhat different notation, because it becomes a bit problematic to really write down all 27.
Are there 27 different functions, or is it 27 different input-output pairs? Because I can think of way more than 27 ways to get 1 to equal 3.
Well, it's 27 different input-output pairs. I mean,
Okay.
yeah, we're not thinking, how could 1 go to 3, but just in the end result, 1 went to 3. So in a certain sense here, yes, we did think of a rule that took 1 to 3, 2 to 2, 3 to 1. But if we don't know that rule, the net result is 1 goes to 3, 2 goes to 2, 3 goes to 1. And if we think of the total net results, there are only 27 possible net results. 1 can go to 3 different places, 2 could go to 3 different places, 3 could go to 3 different places. That's 27 different sets of ordered pairs. And that's another way we could describe a function, just with a set of ordered pairs. So we could also describe a function f from A to B as a subset of A cross B, which is the set of all ordered pairs, such that each A in our domain appears exactly once. So we could describe, say, this function, 1, 3, 2, 2, 3, 1. That's not all of the 9 ordered pairs, but it is a subset where each A appears exactly once. And by and large, I mean, we like this level of predictability. In general, we like to know, if I do a certain thing, exactly what's the result going to be. I mean, it's frustrating, and unfortunately not everything in life works as a function. I mean, you study 2 hours for a test in one class and get an A. So another class you study for 2 hours and that didn't go so well. You think, I studied 2 hours the last time and I got an A. Why didn't that happen this time? Well, studying for a test isn't a function. The same input doesn't always produce the same output. We like the predictability, that if we do a certain thing, we know exactly what's going to happen. And that's the idea of a function. For each input, we know exactly what it's paired with. Now, there was a question somebody asked about, could they repeat? So suppose we don't allow repeats. So if we allow no repeats, how many of these functions are there? I hear 6 from 3 factorial. Because we have 3 choices for where 1 goes, but then only 2 choices for where 2 goes, because we can't, if we're not going to repeat wherever 1 went, we can't use it again. And then 3, well, just 1 place for it to go, whatever happens to be left. And in fact, we've actually have already looked at these a little bit. We didn't realize it at the time, but we had the rigid motions of the triangle, the original vertex 1, 2, and 3. What happens when we flip? 1 stays the same, 2 and 3 flip. So we had in our notation, the flip 1, 1 stayed the same, 2 and 3 reversed. The flip about vertex 2, 2 stayed the same, and 1 and 3 reversed. The flip about 3, 3 stayed the same, 1 and 2 reversed. We had the identity where nothing happened. And we had, let's see, rotation, where, let's see, 1 moved to 2, 2 moved to 3, 3 moved to 1. That may be slightly different than we labeled it the last time. Or if we do the rotation twice, 1 ends up moving to 3, 2 ends up moving to 1, and 3 rotates twice, ends up at 2. And our identity. Now, this particular function, since we are going from a set with 3 elements to another set with 3 elements, when we go no repeats, not only does each input go to a different output, we end up using all the outputs. And in a very real sense, that's really sort of the basis of counting any set of objects. You start counting 1, 2, 3, 4, 5. If you ever watch a little kid count, they might go 1, 2, 3, 4, and count something twice. Or 1, 3, and skip something. There's some things they could do. But the whole idea of counting is we have this idea of what is a matching, what we're going to call a one-to-one and onto pairing. But the one-to-one and onto are 2 different ideas. And not every function has it. I mean, this one's not onto. We don't get all the outputs. Neither is it one-to-one, because we repeat some outputs. So intuitively, one-to-one means we have no repeated outputs. Or different inputs produce different outputs. This book actually terms one-to-one with another term that's sometimes used, injective. I prefer one-to-one, probably because that's the one I learned years and years and years ago. But there are no repeated outputs. Different inputs produce different outputs. So if we see a function, we should be able to identify if it is one-to-one or not. So it's kind of illustrated. I mean, what we did over there, all of those are one-to-one. That's how we built them. We picked an element for where 1 went, then we picked a different one for where 2 went, and whatever was left for 3. So that was one-to-one. We intentionally chose to never repeat outputs. Let's think of a couple other functions, more in a calculus style. So f of x equals x squared, where we're going from the reals to the reals. Do we ever repeat any outputs? As opposed goes to say f of, from the reals to the reals, I guess let me call this g. G of x is x squared.
Would you consider an input of 1 repeating? Put in 1, you get 1, or is that still?
Well, no, repeated outputs, we would need something else to go to 1 as well. So the fact that 1 goes to 1 and this one doesn't give us a repeat, does anything else go to 1?
Okay.
It's negative.
Yeah, so actually here, 1 goes to 1 and negative 1 goes to 1. This function is not 1 to 1. Because we can figure out 2 different inputs that actually produce the same output. Does that happen over here? Is there any way that we could have 2 different outputs without having 2 different inputs to start with? Do you think if we changed the domain we could?
Well, if you could use fractions, because you could get 2 times. Oh, no, you couldn't.
And actually, I mean, fractions are in here. However, what you say about on a different domain, that is something we do need to be concerned with. Because this function here is not 1 to 1 on this domain, but if I change a little bit and go from, say, the positive reals and 0 to the reals with the same rule, this function is 1 to 1. Because I threw out the negatives. In fact, here, for every negative, there's a corresponding positive that does give us the same output. So I just throw out all the negatives, I get rid of that problem of the repeats, of outputs being repeated. So we can kind of watch as we think 1 to 1. It is not just the rule, but part of the rule is, what is our domain and codomain? What set are we starting from? What set are we going to? Now, as we move to more abstract ideas with functions and 1 to 1, this idea of different inputs produce different outputs really isn't the most helpful one for us to work with. Because essentially this would be, if x1 isn't equal to x2, then f of x1 isn't equal to f of x2. For specific functions, that idea is probably sufficient for us. That if we could find 2 different inputs that go to the same output, which is what happened here, then we know the function's not 1 to 1. And with a specific rule, we could probably argue different inputs would always produce different outputs. I think we could here. That if x1 isn't x2, double both sides, 2x1 isn't going to be 2x2. So this function actually is 1 to 1. There's no way we're going to get repeating outputs. Each input goes to something different. Now, the fact that each input goes somewhere is part of being a function. It's the inputs going to different outputs that's related to the 1 to 1. Now, that idea is a challenge for us when the functions get more abstract. Because there are lots of ways things could be not equal. And it's really kind of hard to follow things not being equal. It is much easier to work with things being equal. And so we look at the contrapositive of this. The contrapositive says if f of x1 equals f of x2, then x1 equals x2. If somehow we ended up with the same output, can we conclude that, oh, we had to have the same input? If we can conclude that, then we know the function's one-to-one. Or if we're told the function's one-to-one, we can conclude that. That if ever at any point we end up with the same output, oh, I know I had the same input because the function was one-to-one. So as with all of our definitions, they go both ways. If we can verify this, we know the function's one-to-one. If we're told the function's one-to-one, this is a true statement. So that's one thing we're interested in. Do we ever repeat the outputs? The other thing we're interested in, let me erase some of this. Is onto, or the book calls this surjective. Do we actually achieve all the outputs? As I mentioned with the gradebook function, I can use the grades A through F, but there's no reason, nothing that says I have to use them all. If I don't use them all, the function's not onto. So if we look at this function, what do you think? Is this function onto?
No.
So what output do you think we're missing? I mean, if we're going to say no, there's an output that we missed.
Every odd output.
Okay, so I can't get 3 out of this?
Oh, no, you could, it's 1.5.
1.5. So if it's reals to reals, I can. So this one is onto. But if I changed it integers to integers, what you say is correct. This one is not onto because f of x equals 3 never happens. So again, even with specific examples, it is not just the rule that we're looking at, it's what sets are we being allowed to work with here. I think in calculus we focus more on the rule, that's our function. And we don't worry too much about what inputs can I use, what outputs could I get. We use all the inputs that we possibly can, and we get whatever we get. We're not overly concerned about what inputs and outputs we're allowed to use. Here we're definitely going to be concerned about the inputs and outputs that we're going to be using. And so if we're only using integers, this mapping's not onto because we can't get 3. What about this one? We can't get negatives. This one's not onto. G of x equals -1 never happens. Similarly here, so let me modify this a little bit. Suppose we go to the positive reals and 0. Is that one onto? Can I get every possible output? I see somebody who's...
I would wager so.
You would wager so. Okay. Well, we can't wager, but I'll... So, say we wanted to get 11. How do I get 11?
The square root of 11.
The square root of 11. I mean, there's a sense here With this domain and codomain, it is one-to-one and onto, and so in fact we have an inverse function, a function that readily undoes what the square does. We call it the square root function. So h of the square root of y equals y for any output y. So you tell me where you want to get. I figured out, well, here's a way to get there. The function is on 2. And again, the function is not just the rule. It's what set A and what set B are being asked to work with here. Yes?
What about the 2x and x squared, the f and the h, less than 1? I mean, it makes sense that it is on 2, but something about my brain is wondering.
So what do you mean less than 1?
Yeah, so let's say for the 2x, you have a half, and to get that you need 0.25, but to get 0.25 you need 0.125, and to get 0.125, and it just keeps
Well, in terms of on 2, we only need one step.
Okay.
So 0.5 would come from 0.125, so we can get 0.25 or 0.5 out of this. So we're not taking this back indefinitely, because I mean, if we did the same thing, we wouldn't have to go less than 1. You know, if we're going to go back indefinitely, start with 10, well 5, 2.5. We just bring it back one step.
Okay.
And in fact, that's kind of our more abstract concept. The function is onto if for any b in B there exists an A in A with f of A equal to B. So any potential output actually comes from somewhere.
Okay.
So we're only stepping back once. Tell me the output, can I figure out where it came from? If I can always figure out where the output came from, the mapping's onto. If there's an output where it's like, no, I can't get that output, the mapping's not onto. Now, when we're going to reals, or even subsets like this, we could think of the graph. Let's do the graph of 2x. We know what that graph looks like, right? The line slope of 2. For determining if a graph is a function, anybody remember how you determine if a graph's a function? It was on my college algebra test I gave Monday. Vertical line test. If every vertical line crosses once, it is a function. Well, that tells us if it's a function or not. In terms of what we're looking at now, though, there's actually what I would call a horizontal line test. If we cross at least once, always, the function's onto. Because a horizontal line is, okay, give me that particular output. And if we always cross at least once, that output we get. Where if we always cross at most once, that's what tells us it's 1-to-1. This particular function, reals to reals, was both. the graph idea doesn't work very well if you're not going to reals, or intervals of reals, at least. I mean, if you start putting holes in there, we really can't graph with holes. We expect the graph to have some holes, and it's a lot harder to figure out, you know, where the holes are. But if we've got intervals where there are no holes, then we can at least think the idea of the graph to decide if the function is 1 to 1 or if it's on 2. And in this particular function, the x squared, I guess I called it h of x, depends on our domain. So when we were going reals to reals, this horizontal line crossing twice is what tells us it's not 1 to 1. The horizontal line down here not crossing at all tells us this function is not on 2. And as we change domain and codomain, we can make it onto, still not 1 to 1. We can make it neither, well, I mean, it is neither here. We could make it both. So let's see, if I go, say, the positive reals and 0 to the reals, so only that portion of the graph, it's still not on 2, but it is 1 to 1. Because no line crosses more than once, but there are lines that still don't cross. If I were to go from the reals to the positive reals, including 0, I'm only putting lines up here. It's not 1 to 1, but it is on 2. Every line from the codomain does cross somewhere. In fact, all but one of them cross twice. So we can look at horizontal lines, and then, you know, this one that I've drawn, every horizontal line crosses exactly once, is 1 to 1, and it is on 2. So we definitely, as we encounter problems, have to think it's not just the rule. It's what sets are we working with here, because we will modify that. And in fact, where we're headed long term is really to not even talk about specific functions, but to talk about the abstract concept of a function, or a whole set of functions. And what can we do with the whole set of functions? That, however, will have to wait till Friday. So we started chapter 6 here. I think you can do the A1 through 3, B1, B4, C1, and C4, but the later problems, not so much, because we're really going to continue to push with this idea of function and try to make it more abstract, and not think of specific functions, but just we have a function, or we have lots of functions. What are some of the things we can do with the functions? So see you on Friday. If you happen to come in late, hang around just a little bit.